Last time I introduced the basic idea of a Laplace transform, and this time we'll look at some basic computations, how we compute a Laplace transform, as well as some basic properties of the Laplace transform. So we begin with a function f of t, which needs to be defined for all non-negative values of t. The Laplace transform of f is going to be a new function defined by taking the integral from 0 to infinity of f times e to the minus st with respect to t. Notice that there's two variables in this integral. There's an s and a t. We integrate with respect to t. We're all done. The s's will remain, and we'll have a new function that will be a function of s. For notation, we will use little f for the original function, and we'll often use a capital F for its Laplace transform. We'll also sometimes use the notation L for Laplace transform of f. So let's look at a simple example. Compute the Laplace transform of f of t equal to e to the at, where a here is a constant. Okay, so first just a little notation. Like I said, we'll often use capital letters like big F for the Laplace transform. We'll also sometimes write L, and it's the Laplace transform of f of t, but this thing is now a function of s. So this is kind of complete notation for the Laplace transform, but we'll also sometimes write it in a shorthand notation as something like L of f or L of e to the at. So these are all just notation for the same thing, lots of different ways of writing it. Now, by the definition up there, this will be an integral from 0 to infinity of f, which is in this case e to the at, times e to the negative st dt. Okay? And to evaluate this integral, let's notice a couple of things. First of all, it's an improper integral, so we're going to be dealing with a limit. So it'll be a limit as b goes to infinity, integral from 0 to b of, let's combine those two exponentials together, and that will be an e to the a minus s times t dt. Now, this is just integral of e to a constant times x. So when we do the integral, we'll get 1 over that constant times t, 1 over that constant times e to the constant times t. So this is going to look like a limit as b goes to infinity of 1 over the constant, a minus s, times e to that same power, a minus s t, and then evaluate that from 0 to b. Okay. Now that's going to be a limit as b goes to infinity of, plug in the, well, we have the 1 over a minus s times e to the a minus s b minus e to the 0. Okay. Now notice that the value of this limit is going to depend on whether that a minus s is positive or negative. If a is greater than s, then we've got a positive constant times b. The exponent's going to go to infinity. E to that power will go to infinity. So the whole thing will be infinite when a is greater than s. In that situation, this original integral diverges. On the other hand, if a is less than s, we will have 1 over a minus s times, this will be e to a negative power times b, so it'll tend to negative infinity in the exponent, which will make that whole thing go to 0, and we'll have 0 minus 1, so we'll have 1 over a minus s times negative 1 if a is less than s. We can multiply that negative through and this will be a 1 over s minus a. So our result here is that the Laplace transform of e to the at, and again, remember this is a function of s, is equal to 1 over s minus a, and the domain of this function is s greater than a.